Hey, this is Brock Lemires. We're continuing our study of embedded systems design. In this chapter, we've switched over to programming our MSP430 in C, and we're looking at timers. In this video, we're going to look at how to generate a pulse width modulated signal using multiple timer compares. So let's do a quick review of what a PWM is. So you're going to have a signal, this is an electrical signal, and it is going to have a duty cycle and a period. The period of a digital signal is always like edge to like edge. So it's basically rising edge to rising edge or falling edge to falling edge. And you're going to have a period, whatever. But you're also going to generate a signal that's going to have a duty cycle. And so the duty cycle is defined as the on time, okay? And you can, sometimes you specify duty cycle in terms of a percentage, and that's just basically the on time versus the period. So what percentage of the period is a 1 versus being off, or which is a 0. Actually, and it's not one on versus off, it's on versus total. And so if you think about a 50% duty cycle, that means you're high for 50%, low for 50%. That's a square wave. So that's a perfect square wave. PWM signals usually have a smaller duty cycle, so maybe something like 10%, 5%, 25%. And they're very useful signals because you can use, that's how a lot of motors are controlled. So servo motors, continuous motion servo motors, DC motors, you can use these as control signals, but you can also use them to pulse things. So for example, like an LED, if you didn't want to drive it full on all the time, you could say, I'm going to turn you on for a little bit and then I'll turn you off. Turn you on for a little bit, turn you off. And you could actually get it to a point where it's a little dimmer than if you drove it all the time. And yeah, they're just used everywhere in electrical engineering and computer engineering, and they're awesome. How do you do one with an MSP430? Almost all microcontrollers use the same approach. You are going to use 2 timer compares. We are going to use 1 timer compare to generate a flag when we reach our desired duty cycle, and we will use another timer compare to raise a flag and overflow back to 0 when we reach our period. Okay, so when we get to the time corresponding with the PWM period. Okay, so that's really all we're going to do. When we generate the signal, what will happen is we start the signal we care about as a 1. And then once it counts up and it gets to the first compare value, the interrupt service routine associated with that compare will take the signal to a 0. Then it's a 0 until you get to the second compare, which is where it reaches the final value in the count. And then this interrupt service routine will take it back to a 1. So we kind of have there's kind of like 3 assignments to think about. First is initializing the signal to a 1. Then you set up the timer system, let it go. The first interrupt routine that goes on compare, the first compare takes it to a 0. And then the overflow compare takes it back to a 1. And then from then on out it goes. So we are going to use the special functionality of CCR0 on the MSP430 to dictate the PWM period. And the reason is because if we put the counter in up mode, whatever value we put into CCR0 will be the value that causes the timer to go back to 0 and start counting again. So it's very simple. If we use CCR0 and the timer in up mode, we can actually just automatically generate the desired period. Then what we do is we just got to make sure that the interrupt service routine for CCR0, it's going to take our signal and go to a 1. We will use a separate compare register. Well, in this example, let's use CCR1 just because it's the next one. And we're going to put in a count value corresponding to the time associated with the duty cycle, or the high time, the on time. And in this interrupt service routine, when it fires, it is going to take our signal to 0. Okay, so then we initialize, it goes out 1, there goes 0, then over here, then 1, and then forever and ever. Here's what's interesting about compare 1. We haven't seen this yet, but notice that the counter just keeps on rolling. It gets to the value of CCR1, a flag is raised, and you can go do an interrupt service routine to service the CCR1. But the timer just keeps blasting. It's only when it hits CCR0 in up mode that it goes back to 0. Okay? All right, let's do this. Let's create a PWM period of 1 second. And let's create a duty cycle or on time of 50 milliseconds. And what we'll do is we'll drive LED 1 with this. Now this is 50 milliseconds is really quick. I mean, it's like, It's 1/20th of a second, but you actually can still see it. It's interesting because you wouldn't think you could see something that's 50 milliseconds in duration, but you just see this fast flash on the LED. So it's actually really cool. And then since it's a 1 second period, it flashes really quick and then it waits quite a long time before it flashes again. So we can use our eyeballs to make sure that we're actually doing a PWM signal. All right, so let's use a clock since we're doing stuff that's relatively slow, like 1 second. Let's first figure out the number we want to put into CCR0. This is the period. So I'm going to take the amount of time is 1 second, and we are going to use the equation that it's the period of the clock times the number of counts. So we will take 1 over the frequency, which is 32K, and then we will solve for n. So we're going to do that math, and it turns out that n is equal to 32,768. So that's what we're going to initialize CCR0 at. Then for the on time, it'll be 50 milliseconds. So we do that same equation. We say I want to have 50 milliseconds transpire, and the equation is the period of the clock times the number of counts. We plug in 1 over 32K, solve for n, and it turns out that the number of counts is 1638. So this counter is going to crank from 0 to 32,768. On the way, once it hits 1638, an interrupt service routine will fire. Once we get to the final value, another interrupt service routine will fire, and it'll also roll over back to 0. Okay, let's think about how we do this. Set up the clock. We got to put the timer in up mode. We got to choose a clock. We'll leave the dividers at their default value so they don't impact anything. We'll leave it at 16-bit mode. We need to go down to TB0, CCR0, and load it with 32,768. We got to go to CCR1 and load it with 1638. And those two are going to generate separate flags, separate interrupt service routines. Now, why can they be totally separate? It is because timer B0 has 2 vectors. So it's got 1 interrupt vector associated with CCR0, because CCR0 is a big dog. Okay, it's an important thing. You use it a lot. But look at CCR1, CCR2. Okay, and the overflow. They have to share. These poor guys. They have to share a vector, but that's okay. In this example, we are going to only have 1 interrupt service routine for this vector. And so it's kind of cool because we're using 2 separate vectors, 2 separate interrupt service routines, 2 separate flags, 2 separate, basically, things. Okay, so let's do it. You ready? All right, let's fire up some CCS and get a typing. So file, new CCS project. And let's see, what do we want to call this little buddy? Let's see here. Let's call this C timers compare CCR1. You know what? That's silly. Let's do this. Let's go PWMs, PWMs. Okay. All right. So we got that. We got that. All right. Here comes our program here. Okay, life is good. Okay, so here we go. So first and foremost, let's go down here and let's set up, what is that? Set up ports, okay? We're gonna be toggling LED 1, so we gotta get it ready. So I'm gonna do P1 DIR. We're gonna do a bitwise OR with the mask bit 0. And why did I do that? Because I wanna set P1.0 to output, and that's LED 1, okay? Now, what's the initial value I want to do? I want it to be a 1 this time, okay? Because that's how my PWM signal is going to work. So I'm going to set bit 0 this time. So I'm going to set LED 1 equal 1 initially. And that prepares me to do this PWM. So now I'm going to do PM5 CTL0 to turn on the digital I/O. So I'm going to do a clear. So here comes a clear. I'm going to go ampersand equal tilde. And I'm going to use a mask called lock LPM5, and that'll turn on digital I/O. So that takes it out of low power mode and turns it on. Okay, so we got that. Boom, 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 boom. All right, life is good. Life is good. Now let's set up the timer. Okay, so we're going to go set up timer, and when it's TB0, let's go ahead and use TB0. First and foremost, remember we always got to do this. We always got to write to TB clear in order to reset the counter. So I'm going to do a TB0CTL, that's the configuration register. That's timer B0 control. That's where a lot of settings are to get this timer set up. So I'm going to do a bitwise OR with a mask called TBCLR. You go reset TB0. Now, just one last reminder here. Where am I getting all these names? Well, all these bit masks are defined in the header file, and all these register names are defined in the header file. So if you don't know the syntax, open up that huge header file for your device and look through there. Okay, now what else we got to do? So we've gone ahead and cleared this. It's ready to go. Let's go ahead and set the mode to up. So we'll do TB0 CTL, and we're going to do bitwise OR to set this bit, MC __ up. Now, put into up mode for CCR0. We put it into up so that CCR0 does its special functionality where it rolls the timer back to 0. Okay, life is good. What else do we want to do here? Let's see. We got to choose a clock. We need a clock. So TB0 CTL. We're going to do a bitwise OR with a mask called TBSSEL __ a clock. Okay, very descriptive mask. So choose a clock, and that's 32K hertz. All right, so we got that, and now the only other two things that I need to do are I need to initialize the compare registers. So TB0 CCR0 gets 32,768. So I'm going to go TB0 CCR0 equals 32,768. And now I'm going to do this. I'm going to go set PWM period so I can remind myself what that value is doing. Then I'm going to go TB0 CCR1, and that's going to be equal to what? It's going to be 1638. So 1638. Come over here, set PWM duty cycle. Okay, life is good. Now you look at these registers, remember, these are the actual compare registers, TB0 and TB1. They are separate registers associated with this timer system, and there's actually another one of them, but we're not using it. There's 3 associated with TB0. So we've got TB0 is the timer, and then it's capture compare register 0, capture compare register 1, and there is a capture compare register 2 that we aren't using, but they're separate registers, and they have their own separate configuration register, which is called TB0 CCTL0 and TB0 CCTL1. So you got it when you look in the device data sheet, you see that they have separate configuration registers. Now, why do we care about those? Because that's where you set up the interrupts. So now let's set up the compare IRQs. Okay, so now we're ready to set up the IRQs. First and foremost, let's do CCR0 first. So I'm going to go into TB0 CCTL0. That is the control register, and I'm going to do the local enable for CCIE. So this is local enable for CCR0. Okay. Nice. Okay, now let's do this. I'm going to do TB. Let's clear the. Let's do the local enable for the other one. TB0 CCTL1, and that's going to be CCIE. Notice that's the same bit mask. That's all right. Same bit location in 2 different configuration registers. So this is the local enable for CCR1. And now let's do the global enable. So let's do enable interrupts and turn purple. Come on, buddy. Didn't turn purple. Did I misspell it? __ enable interrupt. Why isn't it purple? Oh, you got to spell it right. Okay, so then we'll do enable maskable interrupts. Now here's what's interesting. This is the first time that we've had 2 separate interrupts enabled. This is big time. So we turned on all the maskable interrupts, and only the ones with their local enable will actually be able to trigger an interrupt. Guess what? We got 2 of these buddies going. So there's 2 of them. So let's do the flags now. Let's clear these flags. So TB0 CCTL0, and I'm going to clear a flag. So I'm going to go ampersand equal tilde. And the flag that I'm clearing is CCIFG. Okay, so I'm going to do clear flag for CCR0. And then I'm going to do TB0 CCTL1. And I want to clear ampersand equal tilde CCIFG. Okay, same flag, that's fine. They're in 2 separate configuration registers. Clear flag for CCR1. Okay, that's it. We have set up a whole pile of stuff. The LED1 port is set up. The timer system is set up, including initializing the 2 compare registers. And then I turned on 2 separate interrupts and cleared 2 separate flags. I'm ready to do a main loop that doesn't do anything. While 1, let's just sit and spin. Okay, so I'm spinning and I'm ready to go. Now, guess what we're gonna do? We're gonna write 2 interrupt service routines. Okay, this is gonna be crazy. This is interrupt service routines. It's such a big deal, I'm gonna spell it out. Okay, now, which one do you wanna do first? Let's do CCR0. We are going to write a routine that is going to go, whose starting address will be put into the vector table. So I'm going to tell the compiler, listen up, compiler, pragma, I am initializing a vector right now, a vector in the interrupt vector table. Vector, which one? Timer 0, B0, vector. Now you got to go, what in the, where did timer 0, B0, which one is that? Let's go back and check, just make sure. Timer 0, B0 vector is what we use for CCR0. So that is the period one. Okay, that's how this is the interrupt service routine for the period. And I can put that there. I can go ISR for period, so I remember. Now I need to tell it, hey, this routine name that I'm about to give you will be the starting address to put in the vector table. But when I do this, I'm going to call it ISR underscore TB0, CCR0, and I do void, just like a normal routine. But I had to put that interrupt in there because I needed to tell the compiler, hey, don't return from this routine with RET, return with RETI. Now we got to sit and think about it. We're all ready to do our functionality for this interrupt service routine, but I got to remember what I'm doing. So I'm at CCR0. Okay, let's go look at our pulse width modulated signal. CCR0 is the interrupt service routine associated with this point in the time. What I want to do is I want to set this signal. So I'm going to set LED1. So I'm going to go in here and I'm not toggling, I'm setting. So I'm going to do this. I'm going to go P1 out and I'm going to go ahead and bitwise OR it with bit 0. And that is going to be turn LED1 on. Okay. Now, am I done? No way. Got to clear that flag. Luckily, I copied it and I pasted it. So boom, boom. Now, this is where it starts getting confusing because you gotta always think about which interrupt service routine are you in. I am in the service routine for CCR0. The reason we came here was because the flag was asserted for CCR0 in the CCTL0 register. Okay, it can, when you copy and paste, especially, is when you get in trouble because you'll forget to like change this to a 0 to a 1 or something when you copy and paste, and it's kind of hard to debug. So if you just think about it. I'm actually going to type out the next one. I'm scared to copy and paste. So I'm ready to do the interrupt service routine for CCR1 right here. So here we go. I'm going to do another. Hey, compiler, pragma, you are now going to initialize the vector table with the following, in the following location. And I'm like, what is it? Well, it's timer B1 vector. And this is the ISR for duty cycle. And it's like, well, let's check that. Timer, well, first of all, I missed timer 0. So it's timer 0, B1 vector. Let's go check. Timer 0, B1 vector. That is right. That's the right location for the CCR1. That's good. Okay, we got it. And now what we're going to do is say, let's write a routine. Not any routine, but an interrupt service routine. Okay, so ISR, TB0, and this is for CCR1, and no inputs, no outputs. What are we doing in here? Well, let's think about our signal. What are we trying to do when we get to this interrupt service routine? We started out a reset at a 1, and then when we get here, we need to take it to a 0. Okay, so let's take it to a 0. So P1 out is going to be cleared, ampersand equal tilde, and I'm going to do bit 0, and this is going to be turn LED1 off. Okay, am I done? No way. You got to clear that flag or else you'll get stuck. So I'm going to copy and paste this thing, copy, paste, and boom. Now I'm going to sit there and look at that. It's like, all right, so let's walk through this one last time before we see if this works. I'm sure there's typos out the wazoo here. Started at 0 by initialization. It runs up to here. CCR1 fires. The interrupt service routine for CCR1 takes it to a 0. The counter is still running, so it's going da, 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 da. It gets to the timer or the compare value in CCR0. So then the interrupt service routine takes it to a 1, and now the timer starts over at 0, and you start over again, and you repeat forever. Okay, let's clean up some typos and then get our board going, and let's rock and roll. Holy cow, there's no time. There's no syntax errors. That almost makes me nervous. Okay, so I got my board here. LED 1 is right there. And let's just see if this works. Let's just go for it. So this is going to be a quick flash if it works. Go. Boom. Yes, look at this. Look at that. Look at flash, flash. Beep, 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 beep. I'm doing the beep in my mouth. That's not actually happening from the board. So we did it. And let's try to look at like the period. So 1001, 1002, 1003, 1004, 1005. So this is awesome. It's proving to me that we have a pulse width modulated signal. I know we're not looking at it with an oscilloscope, but you can see it's a tiny flash and then it repeats every second. So we did it. And it's kind of interesting that that's 50 milliseconds. That's not really a lot. Now, whether or not the light coming out is exactly 50 milliseconds, it might be something where the LED charges up and then discharges. So it might be a longer flash than 50 milliseconds, but it's absolutely being driven with a signal that's 50 milliseconds. Holy cow, you did it. You now, think about what you're doing right now. You just created a pulse width modulated signal. You set up a timer. You had 2 totally separate but related interrupt service routines that were run to generate a signal that you used to flash an LED. That was a lot of stuff going on. So congratulations, that's awesome. And that's it. So as always, support my channel by subscribing and see ya.